Hello everyone, my name is Anthony Shivkumar, and in today's video we're going to do something a little different in the sense that I'm actually going to go right down to the basics of studying and analyzing RLC circuits. And the reason being is when I was trying to design some of these circuits in the previous video, I made a video blog on how it's important for me to write some guidelines on how to design this PCB. And the more I'm studying things like signal integrity and power integrity and EMI and how to design a more robust and reliant board, it eventually keeps dragging me into understanding these concepts. Like, it's an RLC network, it's an RC circuit. The whole idea is, can you boil these the complexity that's happening in the real world into smaller lumped circuit models. And of course, this is an abstraction from, say, using Maxwell's equation and things like magnetic fields and electric fields, and instead of doing all those complex computations, a lump circuit model makes some of those Maxwell's equations a little bit more easier by just using basic differential equations and Ohm's law, and that's why I wanted to create this video, because I just said, I've done this probably 20 years ago. The last time I actually was being tested on this stuff, and it's been a while since I've actually wanted to go down and write these equations and really remind myself, how important understanding how this really works. And so that's what this video is all about. What I'll be doing is I've written some of those equations, and I'll explain a little bit about, just revising as to how all of this works, and then we'll try to put some of these numbers into MATLAB, and we'll also use simulation software like ADS to create these circuits and understand these circuits more into detail. And this is important because as we try to make more of these boards, eventually you'll be simulating all of this through a SPICE model, and the more we're able to capture the parameters of this board into simple lump circuit models, the better it is. So there's an advantage of just understanding this. So let's get started. I have three circuits in here. I have an RC circuit, I have a RL circuit, and I have an RLC circuit. And these are dynamic circuits. What does that mean? You have a capacitor and you have an inductor. And these two components are not a resistor. A resistor, it will be always constant. You put a voltage, it will always behave the same. The current flowing through it will always be, an IR, or the current flowing through it will always be V by R. But as an inductor and a capacitor are based on time, basically. So the current flowing through a capacitor is C dVc by dt, and the voltage that can flow through a capacitor or inductor is L di by dt. And in simple English, it basically says that if it's a DC current, if there's no change in voltage, then a derivative of a constant is constant, so there's no current flowing. So you can almost think of a capacitor only, an ideal capacitor will only conduct when there is change in voltage, and an ideal inductor will only work when there is a change in so it will be an open circuit when there's change in current. So basically, if you keep changing current drastically, so di by dt will be very high, then there'll be a voltage and a potential, and that voltage and potential can cause will be an open circuit. So if there is no change in current, then it will basically just be a normal short circuit. At least this is an ideal inductor. So those they have complementary effects in that sense, and we'll analyze these circuits a little bit more in detail. So what we're going to do is model these circuits into the state space approach, which is basically saying x is equals to ax plus bu and y is equal to cx plus du. So this is a state space representation of a states. So x is generally the derivative of say x, and this could you could apply this not just in the electrical domain, it could be in the physical domain, it could be in the mechanical domain, where you could have, like, say, this is the speed of your car, and your x would be the position. So the position multiplied by the time that you travel will give you the speed of your car, right? The amount of distance traveled in a set of given time will give you the speed. So something of that sort. So this equation is once you reach the mathematical domain, it's kind of universal, irrespective of whether you're coming from an electrical side or you're coming from the mathematical mechanical side or anything of that sort. But in this particular case, we're going to analyze the electrical side of things. So we're always going to represent the state space. We're going to derive our equation in such a way that we're going to be using the state space model. All right. So when we're doing the state space model for modeling this circuit, one thing to keep in mind is find the component that has a state that would have a state variable, and in this particular case is the capacitor. So what I've done over here is just basically saying, hey, we have the capacitor, which is the state variable. The current flowing through a capacitor is C dVc by dt. So that's the variable that is changing based on time. This is the dynamic part of the circuit. And then I've basically tried to say that, okay, C dVc by, and you're also applying things like Kirchhoff's law and voltage law, and Kirchhoff's current law and Kirchhoff's voltage law, in the sense that the voltage across this whole thing, the sum of the voltage across each node will be should be equal to 0. So that means the voltage in minus voltage R minus voltage C should always be 0. And if you have a node, like in this particular case over here, the current flowing through the node will always be 0. So those are the high level principles of how you can model these circuits and create these equations by applying certain principles. And in this particular case, we have C dVc by dt. That means the voltage, the current flowing over here is equals to the current of Vc minus or Vn minus Vc divided by R. So the input voltage minus the output voltage divided by R, it will give you the current flowing through the resistor. And then this voltage that we see over here should be a C dVc by dt. And based on that, we have just basically modeled the C dVc by dt. I've just put a Vc dot. And then we take the C down and we have minus Vc minus 1 by Rc plus V1 by Cv in. And you're basically, and this is the output equation for state space model. So the output is going to be Vc, which is the output is Vc, is going to be 1 into Vc plus 0 into Vn. There's no feed forward circuitry over here, so it's most likely always going to be 0, depending on what's your output and what you're trying to model. So this is the first equation. So let's go into MATLAB and have a look as to what we've done over here. All right, so the first circuit that I have basically taken the variables of A, B, C, D. So just give me a minute. So the way you do this in MATLAB is, all I'm trying to do is 1 minus 1 by RC is the A variable, minus 1 by C is the B variable, 1 over here is the C variable, and 0 is the D variable. And MATLAB understands, A, B, C, D. And then once we understand these A, B, C, D, the values for A, B, C, D, and we can do some analysis over here. So in this particular case, A is minus 1 by RC, so minus 1 by RC. B is 1 by C. B is equals to 1 by C. But I have a mistake over here actually. So the R is always going to be common to both because there's a R over here. So it's going to be 1 by RC, and then C is going to be 1, and then D is going to be 0. Okay, and I've just basically given the value of RA as 10 ohms, and the capacitor is going to be, say, 10 nanofarad. So let's run the simulation. And in order to run the simulation, you can just do a step response, and once you do a step response, it will tell you how the step looks like. So I'm just going to So here we go. So this is the step response. And this is how you can model a simple RC circuit. And what we're going to do is the same thing for an RLC circuit, where I have, once again, we'll go to the equation for the RC circuit. So this is a simple step response. And if I just change some of the parameters, say, for example, if I change C to something smaller, save this and then run the section. Should see a smaller time constant actually. No, actually should be a longer time constant because it's I'm making it bigger in value. So if I make it say 12 into 10 raised to minus 12, then it should be, now it's even more smaller. So the RC time constant should be what's happening? Oh yeah. So you have to look at the grid on the bottom, and the grid in the bottom is actually changing based on the time. So though the graph might look the same, but it's also important to look at the time that it's analyzing, and it's 10 raised to minus 10, which is a much more smaller time. So just though the graph looks the same, which was the thing that I was wondering, why is it not changing? It's important to realize that the x-axis is computing at a much more at a very short interval of time. Okay, so let's go back into a little bit more of the theory. So that's the RC circuit. Similarly, for the RL circuit, what I've done over here is the same thing, where the first thing is to basically analyze the dynamic component of the circuit, which is the inductor. And what is the state variable of the inductor is that the inductor changes. There's a voltage across the inductor only when there is a change in current. So V is equals to L di by dt. So in steady state conditions, if there is no change in voltage or there's no change in current, you can think of an inductor as a short circuit. And as the current changes, it starts to become an open circuit, an ideal inductor. Of course, a real inductor will not have these kind of characteristics. It will still a real inductor will have a little bit of a capacitance and a resistance component to it. Almost all circuits will have this, and that's where the analysis is so important, because when we are dealing with, say, an actual capacitor on a PCB, we have to model it as an RLC circuit because there's a little bit of inductance, there's a little bit of capacitance, a little bit of resistance in the practical capacitor, and we're using this lump circuit model theory to understand, say, the characteristics of that real capacitor. And that's why I'm doing this, because a lot of the analysis in real life and practical life is distilling it down to these types of circuits, because a practical circuit is not a pure inductor, and that's why it's important to do this as well, right? I mean, there are many other reasons, but nevertheless. So continuing with the dynamic equation, so we have V in is equals to the voltage across this particular resistor, which is IL into RL. So current flowing through a loop will always be a constant. It doesn't matter whether there's an inductor, a capacitor, or whatever be it. Current flowing through a loop will always be constant. So I'm taking the current flowing through this whole loop as IL. So IL into R plus L di by dt, because that's the current flowing through an inductor. And we know that over here as the voltage is equals to L di by dt. The voltage across the resistors, V is equals to I into R. And the voltage across inductor is L di by dt. So the total voltage across this whole circuit, as I mentioned, based on Kirchhoff's voltage law, the voltage across the whole loop must be 0. So the voltage of in must be equals to the voltage of R plus voltage across L. So now we basically bring the L to the left hand side and move everything to the right hand side. So L di by dt is equals to minus IL by R plus Vn. And then what we do is we basically get this into this format. That's a state space variable format or the state space model. So we can have this as AX into BU plus CX into DU. And in this particular case, I have it as minus 1 by RL plus 1 by L, which is B. And here this is going to be R, and this is going to be 0. So let's look into MATLAB. I will just basically do a lot of this analysis at a high level, and we'll go back and forth between MATLAB and my theory, and then we'll do the simulations of these models using a Spice software. All right, so now I'm in MATLAB, and now I have the RL circuit. So what I'm going to do right now is I'm just going to clear everything. And let's use the RL circuit. Now the RL circuit, it will be very similar. All we have to do is look at the changes in the time constant. So in here I got a 50 into 10 raised to minus 9 nanohenry. Here we have, say, RB is equals to 50. A is equals to minus R by L. B is equals to 1 by L. C is equals to RB. And D is equals to 0. And all I'm trying to do is basically model. I'm basically putting the inputs based on the circuit that I'm modeling, and this is what we get. So as it looks very similar to the RC circuit, and yeah, that's the idea, is to see how these two circuits behave, because the third circuit, the RLC circuit, will now start to show you what how they can actually interact with this, how they interact, and how the step response will actually change. Primarily because the L and the C can have very complementary effects, and it can cause some oscillations depending on the values you choose and all that stuff. So let's go to the third circuit and analyze it mathematically. And then we will do some studies onto it. So now we have the RLC circuit, and here I got a load at the end just to make the solving of the equation a little bit easy. I won't say easier, but just to make it a little bit more practical in that sense. So we have a RLC circuit, which is all in the loop over here, and we have an RL over here. So the first thing to do when you're modeling a circuit of this sort is to figure out what are the dynamic components, which is the L and the C. So that's step number one. And then what are the dynamic components? So what are the state variables of these dynamic components? So the L will have a state variable of I, and C will and the capacitor will have a state variable of voltage. So the L di by dt. So the voltage across the inductor is L di by dt, and the current through a capacitor is I is equals to C dVc by dt. So this is what we need to keep track of. So there's going to be two equations for the circuit because they're two state variables. So in a state space equation, the amount of the size of your matrices basically will be based on the number of state variables. So that's the reason why we have two state variables, IL and VC, to represent these two. And the two equations that we'll have is L di by dt is equals to VI, which is the input, minus the voltage across the resistor, minus the voltage across the capacitor. So, or we can basically say that the voltage of the input voltage is equals to the voltage across the inductor plus the voltage across the resistor was plus the voltage across the inductor plus the voltage across the capacitor. This is what the input voltage is, and that's exactly what we've done. We just reshuffled everything to get the state variable on the left hand side so that it fits the state space equation. And then we have a second equation where we need to have VC as a state variable because that's the second dynamic component. And here we can say that VC, so this is based on the Kirchhoff's current law, we have all the current flowing through a node must be 0. So dVc, so the current flowing from dVc by dt must be equal to IL minus VC. So we have a IL minus VC by L, and the voltage across L is nothing but the current flowing through this particular branch is nothing but I is equals to V by L, and this particular case is VC by RL. And this is where we have the dynamic equation. And then all we're going to do is just put this into the state space form. So we've basically got IL and VC minus RL minus 1 by L, 1 by C, and minus 1 by RC, IL, VC, and into the input. Now, I'm not gone into a complete. I mean, you're not going to view this video based on me teaching you this stuff. There are many other videos out there, and you probably want to take a course from Coursera or from NPTL, where they will rigorously test you on this stuff. That's where you should be learning this stuff from. The reason why, what I'm trying to show you over here, or the reason for this particular video, is more about first and foremost for me to really revise what I've taught and what I've learned actually before, and also to basically give an connect the dots between what's happening over here into what I'm really doing with designing my drone, and why all of this theory is suddenly very important, and why it's hitting me back when me being rusty is not a good idea. Understanding this from a deeper level can actually help me propel further away when I'm designing some of these circuits. So that's really the high level stuff. Okay, so let's go back again to MATLAB. So here we have an RLC circuit again. So now I'm going to clear everything. And let's do the RLC this time. So I've also put in all the numbers. And here we see the dynamic effect of an RLC circuit. Now, if I change the components, so if I change one of the load resistance, I can flatten these things out. And say now if I do a now we can have a very similar step response. So you can see that the RLC circuit, based on the components and the values that I change, even if I just change the resistance value of the output from 10 to 100, suddenly can have a very dynamic effect to the system. Now, I also want to mention something that before we go in to do the SPICE model, is when we analyze our circuits, there are three ways where we can analyze our circuits. One is the time response, which is what I'm showing you through MATLAB, which is the step response of the circuit, right? So what we're doing in the time response is I give a step response, and then I might see some form of step response. Second thing is the frequency response, and I'll show a little bit about the frequency response shortly, where you can see the phase and the magnitude of the circuit. And what a frequency response does is that it takes a sweep from say 0 hertz to all the way to say however you want, 50 kilohertz, 50 megahertz, 50 gigahertz. And it'll show you how the system is responding, what's the magnitude of the system, and whether there'll be a phase lag with the system, and how does it respond as you change, as the frequency of the system changes. So it basically does a frequency sweep, and then it models the circuit based, and it models the basically the circuit and its behaviors. And then we have something called as a pole zero analysis, which allows us to understand the dynamic impact of this whole circuit. And the pole zero analysis will really give us more into, how much oscillation is there, will there be any oscillation? Though all of this is happening in real life, everything is happening in the time domain. But these are the different ways in which we can analyze the circuit so that we have a better understanding of the stuff. For the most part, for signal integrity, I'll most likely be focusing on time response and frequency response stuff. But if I'm trying to design, say, an SMPS, and I want to, make it as robust and reliable as possible, based on what the input signal is. Say if you want, output of 12 volts, and I want it to always be 12 volts, no matter whether there's a surge in the input, whether there's a dip in the input, or whatever be it, then the understanding of pole zeros will be very important, because you want to have your control systems really try to, give you a very steady output, and having an understanding of how your system is responding without these oscillations. You want to minimize these oscillations, you would need to have a better and thorough understanding to the pole zero domain. So to give you an idea of what we have over here, so for the same circuit, if I do a bode, of ABCD. And here we can do a grid. Yeah, you'll be able to see that on the x-axis you have the frequency. So it's going from, say, 10 raised to 5 hertz or radians per second in this particular case to 10 raised to 8. And here you have the magnitude, and it'll also give you, the frequency or the resonant frequency at which, it starts to peak. And then from there on, as you increase the frequency, then the magnitude decreases quite significantly. So this is one way of looking at it, and it will also tell you the phase shift based on, as the frequency increases, there'll be a phase between the input and the output, how it's behaving. And eventually, as you increase, there'll be, as the frequency increases, the phase shift or the degrees will be minus 180. So it gets kind of unstable as you increase the frequency. And in this particular case, it'll be 0 with lower frequency because the phase shift is 0 over here. Another thing we can do is called the PZ map or PZ map, and I can do an A, B, C, D, and the pole zero analysis. And I can do a grid over here. This is important when you're doing control system theory. But in this particular case, you can see that there are two complex poles. You'll always have poles on the left-hand side. And what this pole zero analysis in a nutshell help us understand is that if there's any disturbance to the system, how long will it take for the disturbance to die out? So it'll always be on the left-hand side of the plane. And if there's anything on the right-hand side, that basically means that if there's a disturbance, then the system will always grow over time. And that will be an unstable system, but there's no practical system that actually works that way, because that would also mean that you're getting free energy, which is basically, you disturb something and all of a sudden you're just constantly increasing the dynamic, the system just keeps getting more and more energy. So you'll never have a right-hand side. It's an unstable system. It'll eventually break if the disturbance keeps growing. So you'll always have a left-hand side, a pole zero. So it'll always be left-hand side. And in this particular case, if it's not on the x-axis, that means you have complex poles. This shows that it's a dynamic system, that there's a lot of oscillation. There's some oscillation. And that's how you interpret this pole zero map over here. This is more important, as I mentioned, when you're studying control systems, and you want to design a proper controller to control your, say, SMPS or any electronic circuit in this particular case. This is where it becomes extremely helpful to understand from a pole zero standpoint. So that's about it from the MATLAB standpoint. And this is where, just analyzing the mathematics behind it is really helpful. And it gives a better intuition of, if I play with the numbers, how it's going to work. So now we'll move into the SPICE model. And from the SPICE circuitry, we will be able to, model the exact same circuit using SPICE. So what I'm using over here is ADS. Which is an advanced design systems from Keysighht. And in this particular case, what I have over here are the three circuits that I just have, which is the R, L, and C over here. Okay. And what I have over here, so we'll just go one step at a time. I have modeled the R over here as, what I'll do over here is say, I'll put another R over here for the C circuit. Rotate so that the circuit is exactly as per the model that I've drawn on the paper. And this is ground. Was it connected? I think it was connected. Okay. So what will we have over here? So let's go by one circuit at a time. So the first circuit that we have is the RC circuit, which is very similar to what we have had, what I drew. And the values that I have in MATLAB is we have R is equals to 10, and then we have your e raised to minus 12. So that's 10 e raised to minus 12. So what we have over here is 100 nanofarad, and here we'll just put this as 10. Okay. One thing to note with something like ADS is to know whether you're doing a transient response. You need to know how quickly is your step response and your stop time, so that it gives a good because it's simulating based on your if you don't specify this, and if you put a very wrong a large number, like even 1 second, because you're doing transient response, 1 second is a huge number when it comes to these types of analysis. You can take a long time to simulate, because we are simulating at picoseconds. Anyways, so what I'm going to do is run the simulation, and once it's done, we should be able to see the circuits. All right, so this is what it opens up. So what we have over here is, I'm just going to do this, and it'll open up what I'm trying to look at. So I've got we'll just do a V in, which is an add over here, and we'll have a V cap A, I believe, add, and let's look at the circuit over here. Input here is minus 0.1. We can put this as minus 1. Yeah. And let's put this as minus. And just to make sure that we have the right thing, so this is C2. So I need to make sure that I'm using C2 and R and V and B. Okay. So I need to make sure. So I need to delete this, because so we have a V and B, and we can B. Okay, so yeah, so using the SPICE simulation, we have a step response, and then we have a very similar response from the capacitor. This is how long it takes to charge the capacitor. So that's what we have in the VNB and VCAP B. So similarly, I'm going to basically add the same thing over here for, I'm just going to basically label this, and this is going to be V underscore IN save A. In this particular case, should actually put this as B, and leave this as A actually. Yeah, that's more accurate. And I'm going to put this as say the voltage across I'll just put your V out B. All right, and similarly we will have here as V in C, and apply, and here we have here as V cap C. Apply. Okay, I'll simulate the circuit again. Yeah, And the reason why we have this problem is because I have to read this and delete this, and let's go to recap A and V in A. And that's what we have. So this is the first circuit. Let's do the second circuit. And for the second circuit, we have V in B and recap B. Actually, that's not right. V out B. Okay, and this is something that needs to be looked at. So we have a pulse of 0 to high. Okay, yeah. So what I'm going to do is I'm going to remove this. I'm going to take this and try to use exactly the same parameters that I have over here. And let's run this. So the whole idea was that it's pulsing, and it's pulsing a little too much, and that's the reason why and we're dealing with this in nanoseconds. So it's very important to do some consistency check, making sure that when you're simulating, we have some form of idea of what we're simulating. And this is to make sure. Okay, so what we have here, V in B and V out. Why is V in V out B? Am I missing something? Okay, so this does not necessarily look right to me. So what I'll do is V in B and this B out B. This is not looking right to me, because first and foremost they should be it's this is not one. Okay, so this is not there. That's 1 nanohenry. That all looks nice right to me. Yeah, so for some odd reason, this graph is not particularly, at least I'm not spent time understanding what's going on. It might be right, but my intuition says that how come a step response of 0 1 suddenly give me a voltage of 10 volts over here. And is this 1? So V out. Okay, so this is V in, which is 10 raised to e raised to minus 12. Aha, okay, I may know the reason. I'm going to put this as 1 nanohenry. Yeah, so this analysis, I need to look into what's going on over here. Let's go to the third analysis, where we have V in C and V cap C. I believe the second analysis has got to do with the time, and there's something with the time that I have that there's something wrong with how the timing is, and I need to understand that. There has to be some consistency check. All right, and then the third circuit that I ever have, I'll just put this over here, which is for the RLC. We'll put here V in C and V cap C, and then let's see what we have over here. Okay, so this is now a little different from what we showed on MATLAB. So what I'll do over here is use very similar values. So this is 100 ohm, I believe. This can be, I think, 10 ohms. C will be, and here these are variables, and variables you can put them over here. So the variable that we have over here is C is 100 picofarad. Let's see what we have over here. So what I'll do is make this as 1, 2, and then so this is going to be maybe 1 picofarad, and this is going to be, say, 100 nanohenry, and 100, and let's put this as one of the reasons when I'm doing live streaming and I'm using this software, it takes a toll on my computer. So I really cannot, analyze as well as I want to. But you can already start to see that it's starting to. So now we can see the dynamic response over here. So as you can mention is, So what I would try to do is 0 to 10. I will try to make the step time, the max step time, stop time can be a little smaller, maybe just 100 nanoseconds, just to see. Let's see how that works. Yeah, so this is a little too small. Let's make this 100. I may have to, this is, I can make the step time maybe a little smaller. It's going to take a little while now to simulate. So this is where consistency step is important, because sometimes the simulation is giving you the right results, but your timing, because these are happening in microseconds, nanoseconds, and if you're not really careful, the graphs might not make sense, and then you realize, oh, I have a, my x-axis and y-axis is way off, something of that sort. So now we've got this a little smaller. So the second graph, I still need to do some consistency check over here to make sure what's going on. But in this particular case, I'm able to, at least for a certain time period, I'm able to get the, at least I know there should be some oscillations based on what we've modeled, but the values are not exactly the same as I've done in MATLAB. And the reason being is because some over years, nanofarad and picofarad, and my simulation is also running in a little different time interval. Whereas MATLAB, I was just able to, put in the numbers and it will work. Whereas here it's doing a little bit different. It's, looking at every instance of time, and it's trying to sample based on every instance how the circuit would behave. So it's the time and the rise time, the sampling time, and the amount of time that I want to sample for is very important. And the bigger the number, the longer the simulation is going to take. And my values are a little bit off over here. That's what's causing the problem. But I could try to make it kind of work. By playing around with the numbers. Now there's something called tuning as well, which allows me to basically just change all these numbers on the fly, and it will real time simulate. I do believe it will take a little Yeah, so now we're getting a very, very clean response time over here in this particular RLC circuit. And if I wanted to be have some form of oscillation, I'm just changing the value of the inductor. Now, this is not the right way to analyze it at all. Ideally, what I would do is actually do some of the calculations on hand, see what I'm really expecting, do my analysis in MATLAB, see my pole zero analysis, and here you can see a lot of the oscillation. And then from there, get an understanding of, okay, what's really going on. And then use the SPICE model to see, okay, what is the circuit doing? That's really how I would go about doing it. And just using pen and paper is not a bad thing, especially when you just got resistors and inductors to get the things working. You can literally hand calculate a lot of this stuff. So yeah, that's in a nutshell how I've been basically trying to navigate all the complexities when it comes to PCB design, signal integrity, power integrity, and EMI. Yeah, so I hope you enjoy this video, and I hope it inspires you to perhaps get your hands dirty and go right to the basics of how RLC circuits work. Use the tools that we have in today's, and say what we have today are very sophisticated tools that can really help you understand this at a much more deeper level. And when you're doing any of this kind of circuitry, you'll realize that a lot of these concepts are still boiled down into the lump circuit analysis, and having an intuitive understanding of it. Just writing the equations with your own hands suddenly, it will suddenly enlighten you. Will open up your mind and realize, okay, now I understand what's really happening. So just an exercise that, if you want to do it, I think it's totally meaningful. All right. Having said that, if you like this video and if it's inspired you to actually do this equations by hand, please do subscribe. Do also like this video. And until next time, there'll be a lot more of these low-level videos while I'm trying to design the circuits. So stay in tune, and if you subscribe, you'll be notified when I release a new video. Thank you so much.